Good morning. We're going to investigate some problems using Newton's second and third laws today. And all you need to do is follow along, take the notes, and do the math as I do it. And when you're finished with this, it will be actually stapled to your Newton's Laws video extravaganza packet that you've already done. So this is just going to be in addition to that. All right, so let's look at the first problem that we have. That is a very poor drawing of a golf club and a golf ball. And I have given you the golf ball's mass, and I've given you the golf ball's acceleration. And I'm asking you, what's the force on the golf ball and what's the force on the club? All right, well, first of all, we know that Newton's second law tells us that acceleration is equal to net force divided by mass, or that net force is equal to mass times acceleration, or you can actually even solve for mass also. Okay, in this particular case, we're going to be looking for the golf ball's force, the net force on the golf ball. And so that's going to be the mass of the golf ball, which is 0.25 kilograms, times the golf ball's acceleration, which is 150 meters per second squared. Okay? All right. 0.25 is 1/4. What's 1/4 of 150? I think it's 37.5. 4 will go into 15 3 times. And you're going to have a 2 left, bring down a 0. Yep. All right, so the force on the golf ball is 37.5 newtons. Now, what is the force on the club? Well, this is an interaction between the golf ball and the golf club. And if you remember Newton's third law says that for every action there's an equal and opposite reaction. If one object exerts a force on a second object, then the second object exerts an equal and opposite force back on the first. So if the golf club exerts a force on the golf ball of 37.5 newtons, causing it to accelerate, then the golf ball also exerts a force back on the golf club that is equal. Okay? So the golf ball, force on the golf ball, we'll call that F of G, is 37.5 newtons. And that is equal and opposite to the force, oops, let me move it a little bit, the force on the club, which is also 37.5 newtons. Now, they're equal in magnitude and opposite in direction. Okay, so the point being that if you will pay attention to Newton's second law, which says force is equal to mass times acceleration, or acceleration is net force divided by mass, you can calculate force, mass, or acceleration using those formulas, but also you can figure out what the force is and potentially what the acceleration is on the other object that's involved in the interaction. Now, you can't tell me what the acceleration in the opposite direction of the club because I haven't given you the club's mass or anything, and that would make a difference. Okay, but let's go down to the second problem. And this time we have a rifle that's being fired. We have the bullet leaving the barrel of the rifle, and it is a 0.01 kilogram bullet, and the acceleration of the bullet is 5,000 meters per second squared. Now, it doesn't leave the barrel going 5,000 meters per second because it doesn't get to accelerate for an entire second, okay? But that is its rate. If it could accelerate at that rate for a whole second, its speed at the end of it would be 5,000 meters per second. Now, it's not because, like I said, it's only in the barrel for a tiny fraction of a second. Okay, but I have the mass, and I have the acceleration of the bullet. Mass, I'll put a little b, mass of bullet. So the net force on the bullet is the mass of the bullet times the acceleration of the bullet. Okay, so that's going to be 0.01 kilograms times 5,000 meters per second squared. And really, this is 0.01, that's 1/100th. And really, that just tells me I need to move this decimal to the left twice. So the force on the bullet is 50 newtons. Okay, and which way? It's oriented this way because that's the way that the bullet is accelerating. So the force on the bullet exerted by the gun is 50 newtons. And then Newton's third law tells you that the force on the gun exerted by the bullet actually has to be equal and opposite. So the force on the gun is equal to 50 newtons as well. And this time, we can actually figure out what's the acceleration of the gun back towards your shoulder, for instance. If you've ever fired a rifle or a shotgun, you know that it will recoil and hit your shoulder. Obviously, it doesn't hit you at the speed that the bullet would hit something else because the mass of the gun is much, much, much larger than the mass of the bullet. But anyway, here we go. So if I want to know the acceleration of the gun, remember I put a little g just to indicate that I'm talking about acceleration of the gun, that is going to be the force, the net force on the gun divided by the mass of the gun. And I have the mass of the gun right there. So the acceleration of the gun is 50 newtons divided by 5 kilograms, and that is 10 meters per second squared. Now again, that acceleration only occurs for a very, very short period of time while the bullet's in the barrel of the gun. But there you have it. When you guys take tests and do these sorts of problems and think through these, the thing that is commonly forgotten is the fact that in this interaction between the bullet and the gun, or the golf club and the golf ball, the forces have to be equal and opposite. The accelerations are not going to be equal because the masses are not equal, okay? But the forces in that interaction are equal and opposite. That's Newton's third law. Okay, the next situation, we have a rocket blasting off into space. And actually what's happening here is the combustion of the gases within the rocket are being forced out the bottom of the rocket. So the forces on the gas to expel them this way is equal and opposite to the forces that the gas exerts on the rocket to propel it upwards. So these two are equal and opposite. Okay, sorry about that. Okay, so the force by the gases on the rocket to make the rocket go up is equal and opposite to the forces that the rocket exerts to push the gas out the bottom to make the gases go down. Now, I put on here that the rocket is 10,000 kilograms and that it is accelerating at a rate of 1.5 meters per second squared. So the force on the rocket is mass times acceleration. So the force on the rocket is going to be 15,000 newtons up. So Newton's third law says for every action there's an equal and opposite reaction, meaning that the forces on the gases to cause them to accelerate downward, that's also going to be 15,000 newtons down, equal and opposite. So you're using second law to use the equation force, mass, and acceleration depending on what you need. And then you're recognizing with Newton's third law that forces are always equal and opposite, that whatever your force is on the rocket, it has to be the same force on the gases. So forces are always equal and opposite. Okay, last one. We have somebody kicking a soccer ball. The soccer ball is 0.3 kilograms. And this time, the force on the ball is 300 newtons. Okay, if the force on the ball is 300 newtons, then the force on the foot is also 300 newtons, okay? The acceleration of the ball, remember you find acceleration by saying net force divided by mass, okay? The force on the ball, 300 newtons, divided by 0.3 kilograms. And that is going to be 1,000 meters per second squared. Now, obviously, the ball does not wind up going 1,000 meters per second because the interaction between the foot and the ball takes only a split second. So it's only going to accelerate at this rate for a teeny tiny fraction of a second. Okay? All right, but you use Newton's second law to figure out your acceleration. And then recognize that the third law says that forces are always equal and opposite. Okay?